Hi everybody, welcome back. Here we are in section 9.9 of AP Calculus BC, the final section of Unit 9, finding the area of the region bounded by two polar curves. Only one more unit to go after this, and then we are at the end of the course. So here we go. Let's wrap up Unit 9 first before we start dreaming of Unit 10. So a lot of times we'll run into situations where a region's not just enclosed by a single polar curve, but rather by two polar curves, which you can see in the picture over here to the right. To determine the area of a region bounded in this fashion, we're going to use the formula area equals integral from alpha to beta of 1/2 r sub 0 squared, where r sub 0 is this radius, the outer radius, and r sub 1 is the inner radius. So if you imagine what's going on here, in reality, you're taking this radius here, the outer radius, and you are finding the integral 1/2 the integral from alpha to beta of r sub 0 squared d theta. That's giving you the area inside of this red curve here. And then you're subtracting away from it the area inside of the blue curve, which you're going to find by taking 1/2 integral from alpha to beta of r sub 1 squared d theta here. And then you can factor out and combine those into a single integral to take, this is akin to the leap that we made when we were finding, area under a single curve in Cartesian form to area between two curves in Cartesian form. A lot of times when we're doing this, it's challenging to figure out exactly how to arrive at the desired area. So it's important for you to look at many situations and how we can adapt our model and our limits of integration to make sure we find the correct area for a particular enclosed region. So we're going to walk our way through this, and I'm going to help us out here a little bit in this section. Let's go ahead. We're going to look at example 1. In example 1, we're trying to find the area that lies inside r equals 3 plus 2 sine of theta and outside r equals 2. And I've already graphed that region on here. I've graphed it from 0 to 2 pi on the grid from -6 to 6 in both directions. Now to help us with this, I'm going to move away from my calculator here for a second and look at a bigger picture of these two curves. We're looking for inside r equals 3 plus 2 sine of theta and outside r equals 2. r equals 2 is the little circle here, and the 3 plus 2 sine of theta is this close to circle, the bigger of the two pieces. So we're looking for what's inside the bigger of the two and outside the little circle. And so if we look at this, that means it's inside this, but outside the circle, which means that the region that we're trying to find the area of in this case is this region right here. Okay, and for this region right here, if I take any segment from the origin out through this region, you see that for this segment right here, the fuchsia colored curve is the outer curve, the blue colored curve is the inner curve, and so this is going to be our outer boundary, and this is going to be our inner boundary. And you notice that happens all the way around. If I take a line out to here, or a line out to here, or here, or here, or here. So everywhere on this region, that same relationship holds, which means this is going to be just one integral. And the other thing that you should notice from this picture is that our integration is going to start right here where these two curves intersect. And it's going to end right here where these two curves intersect. So I'm going to need to find those as my limits of integration. So let's go ahead and do that using our calculator. So there's my outer curve, my inner curve. That holds true the whole time. So I'm going to have 1/2 times the integral of 3 plus 2 sine of theta, quantity squared, minus 2 squared, all with respect to theta. And now I need my limits of integration. So I'm going to go ahead and trace my curve. Unfortunately, I can't get down to this point here where I'd like to. I can go all the way around to that point on the curve. If I go all the way around here, I can get to this point. But if I do that, I've gone, the whole way around here. I probably want to go in the negative direction. So a little trick I can use to do that, if it helps you, is I can go in here and change my window. And instead of starting at 0, I'll start at -pi/2, since that takes us down there below. And I'll regraph this. -pi/2 is definitely going to get this for me. All right, so now I'm going to trace. And looks like that's the first intersection point. And I toggle back and forth between the two curves, and it is. And I recognize that that is -pi/6, so that's going to be my lower limit of integration. And if you know how these trig functions work, you should already know the other limit of integration. But if we go over here to where the two curves intersect again, there it is. That is at 7pi/6. So that's going to be my upper limit of integration. And now I'm going to just go ahead and calculate. So I've got 1/2 times the integral of the quantity 3 plus 2 sine of theta, quantity squared, minus 2 squared, all that with respect to theta, from -pi/6 to 7pi/6. Ooh, I want a decimal. It gave me an exact value pretty darn quicker than it gives me a decimal. Maybe I should have just, instead of letting it integrate again, I should have just converted the 33√3 plus 28 pi all over 6 to a decimal. That gives me an area of 24.187 for that region. All right, part B. Part B, determine the area of the region outside the bigger curve and inside the small circle. So let's go ahead and clear our annotations off that. So what are we looking for again? We're looking for outside the big piece and inside the small circle. So we're talking about this region right here. There's the outline of our region. We're talking about this region here. If you think about this from the, from the pole, any segment going out from here looks like this. The outer curve now on this region is the circle, and the inner curve is the other curve. And then my limits of integration are going to be here. There's where it starts, because we're going around the circle. And we start here, and then we continue on over to this limit of integration here. So the circle is going to be the outer curve, and the other curve is going to be the inner curve. So when I write my integral, this is going to be 1/2 times the integral of circle minus the other curve. And then I need my limits of integration. And so I'm going to go ahead and trace my curve. Oh, we already had that one, 7pi/6. And then it goes over in this direction. Oh, until we get to that negative pi over 6, which is equivalent to 11 pi over 6. So that's my other limit of integration. Now let's go ahead and calculate the value of our area of our region on our calculator. So we've got 1/2 times the integral of 2 squared. I guess I could just write 4 there instead of typing 2 squared, but I'm a creature of habit. Quantity squared with respect to theta from 7 pi over 6 to 11 pi over 6. And we'll let it calculate. And that's 2.196, 2.195, also acceptable. Let's see if we can get through this last one first here. All right, example 3, determine the area that is inside of both curves. This one gets a little tricky for us. Inside of both curves. So it's inside of this one and inside of this one. And so we're talking about this region right here being our region. Now notice if we draw sections from the center, when those segments are here, we're just going to the circle. When the sections are down here, we're going to the other part. So starting here and going around, we're going to have one integral. And then starting here and going around, we're going to have another. All right, so that's negative pi over 6 to 7 pi over 6 inside of the circle. So we've got 1/2 integral from negative pi over 6 to 7 pi over 6 inside of the circle. And then from 7 pi over 6 to 11 pi over 6, starting here and going over to here, it's just the curve to the 3 plus 2 sine of theta. So we've got 1/2 times the integral of that, 3 plus 2 sine of theta. And we add those two regions together. If you look at the graph here, we add those two regions together. The region formed here by using this curve, and the region formed here by using the circle. And that gives us the area of the whole thing. And so now that we've got all that set up, all we need to do is go ahead and punch it up on our calculator. 1/2 times the integral of 4 with respect to theta from negative pi over 6 to 7 pi over 6 plus 1/2 times the integral of the quantity 3 plus 2 sine of theta, quantity squared with respect to theta from 7 pi over 6 to 11 pi over 6. And we punch that up, and hopefully my calculator will do all of this. Hey, there we go, 10.370 is the area of that region. So you saw a couple of different things, a couple of different regions we could find the area of that were related to the same two curves, and the different kinds of thought processes that needed to go into all of those different regions. All right, we'll come back next time for the second and final video of this section, and then we will be done with Unit 9. All right, have a great rest of your day, everybody. See you when I see you again. Bye-bye.